Hello everybody, and welcome to the video lecture for Lab 11. This lab works with harmonic motion. Harmonic motion is one of, if probably not the most common source of motion in the entire universe. It affects everything. Today, we are working with motion, and we are seeing, for a simple pendulum, does the density of the object with mass, we have a little wooden ball and a little brass ball, affect the motion? Does the length of the string affect the motion, the length of the motion itself? And finally, how does the angle affect the harmonic motion? All of these we're going to be measuring the period. Do the periods get longer or shorter, and why? So, for the first part of the experiment, we have both of these set up at a short distance of 15 centimeters, 20 centimeters, my bad. And we would simply collect data by offsetting it a small amount. Do note that for the first experiments, we are using small angles. For anybody who doesn't know, the equations for a simple pendulum are an approximation. The full equations come from a complicated Taylor series that you will eventually learn in analytical physics down the line if you ever take it. So we have to use small angle approximations, which we will then see break on part B. So we would simply extend the angle out 5 degrees, as it says, and then let it go. And then we would count out 10 rotations. 2, 4, 6, 7, 8, 9, 10. And then you would divide that by 10 and have a good estimate for the period of your simple pendulum. You would then unwind it out to the next measurement that it states in the lab manual, and you would record again. And so all we're doing is recording 10 periods, dividing by 10, and then extending. And then we do the same thing for the wooden ball. So all these results will be recorded so you can appropriately see how the effects of changing material matter. And the biggest effect for these materials in real life, we're not in a vacuum, we have friction. So this is less dense than this. So this overpowers the air resistance a little bit more. It slows down a little bit less over time. So you might see those results in the data we have collected. For the second part, we use non-small angles. We use 30 and 45 degrees respectively for both balls. So we take it out to 30 degrees, which is here, and then release. From there, we would do the same thing where we count out 10 full rotations, and then we would stop and divide by 10 and calculate it. And a part of the data is we have the period, the calculated period, and the corrected period. This will be in your lab manual. Here is the simple period. Here is the full Taylor series, or not Taylor series, just a full extension. It can be approximated using a Taylor series. We will only be using the sine squared term. Everything past here we can ignore. We're just going to do 1 plus the sine squared. And you will see that at large angles, the corrected formula gives you a lot closer than the simple one. So whenever you do your number plugging, your period is what you actually measure. This is correct. You are not correcting this one. Leave this one alone. The calculated period, this is what you'll calculate using the simple pendulum equation. You will then plug this t into the corrected. I mentioned this specifically because in the corrected formula, it has t naught. This t naught is the t you get from this equation. It is not the t naught that is your actually experimentally verified equation. You are not correcting an equation you found experimentally. It doesn't need a correction. We're correcting our wrong equations to match real life. That should be it. Have a nice day.